Welcome to this explainer. Today, we're putting on our detective hats, but, instead of dusting for fingerprints at a crime scene, we're diving into a microscopic mystery. We're going to explore how we use computerized matching of spectra, specifically using powerful algorithms to compare digitized mass spectra against massive databases to identify completely unknown substances.
Okay, let's dive into this. Picture this scenario. You're handed a vial of a clear mystery liquid. It looks exactly like water. But you know from its physical properties, say you've already observed that it boils between 158 and 159 degrees Celsius, that it is definitely not water. So how do you figure out exactly what it is? Obviously you can't see the molecules, and you absolutely do not want to rely on tasting or smelling it, right? We need a way to literally see the invisible.
Section 1. The chemical fingerprint.
And this brilliantly illustrates our first step. To get a fingerprint of our unknown liquid, we turn to a mass spectrometer. We bombard the sample with high-energy electrons, which essentially shatters the molecules into smaller fragment ions. It's kind of like smashing a vase and looking at the pieces. The machine then sorts these fragments by their mass-to-charge ratio and creates the graph you see right here, a mass spectrum. Every single chemical compound breaks apart in its own highly unique, reproducible way, which gives us a perfect digital fingerprint.
Section 2. The digital library. But here's the thing. Having a perfect fingerprint is completely useless without a database of known suspects to compare it to. A fingerprint without a suspect list doesn't actually solve the case. And that's exactly where the Spectral library comes in. This is a digitized database containing tens of thousands of reference mass spectra. Because of modern PCs, we don't have to manually flip through massive reference books anymore. We can just bounce the digitized spectrum of our unknown sample against tens of thousands of these known datasets in mere seconds. It's essentially a lightning-fast automated lineup for chemicals.
Section 3. How the algorithm works.
So what is actually happening when the computer runs that search? Let's open up the black box here to see how the computer thinks. The search algorithm takes a few very logical, sequential steps. First, it categorizes each peak in our sample's spectrum by how unique and how abundant it is. Second, it assigns different mathematical weights to these peaks based on their mass. And third, it calculates a final probability score based on how well the peaks in our sample match the peaks in a given library reference.
So the crucial point is that second step, weighting heavier mass peaks more heavily. Now, you might be wondering, why does the algorithm do this? Well, small, low-mass fragments are super common across thousands of different, totally unrelated chemicals. They're basically background noise. But the heavier fragments, the ones with a larger mass, those are much more characteristic of our specific compound. The algorithm knows that the heavy pieces hold the real clues, so it prioritizes them during the search.
Section 4. Analyzing the hit list.
Okay, the algorithm has finished running its massive comparison, so let's look at our suspects. Now, what's really interesting about this slide is the actual hit list the computer spits out for our mystery liquid. It gives us this beautifully ranked table showing the name, molecular weight, formula, and, of course, that all-important probability score for each potential match. Notice how the molecular weights and formulas are totally identical for the top contenders?
But look right at the top of that list. We have a 94% probability match. The algorithm is incredibly confident that our mystery liquid, the one boiling at 158 degrees Celsius, is a compound called 1-chloro-2-methylbenzene.
But check out the immediate runner-up. The second suspect is 1-chloro-3-methylbenzene, coming in with a 70% probability. These two chemicals are isomers. That means they have the exact same molecular formula of C7H7Cl and the exact same molecular weight of 126. Their atoms are literally just arranged slightly differently on the ring. The algorithm is smart enough to differentiate between them by meticulously comparing those tiny variations in their peak intensities that we talked about a minute ago. Let's move to Section 5 and see how this builds into the human element.
This brings us to the final, and I'd argue perhaps the most important phase of our investigation. We have a 94% match from a highly sophisticated piece of software that just searched through tens of thousands of records in seconds. So I gotta ask you, does this high probability score mean our chemical detective work is officially over? Is the case closed?
The answer is a resounding no. As our source material explicitly warns, and I'm going to quote this directly because it's absolutely fundamental to good science, it is tempting to simply accept the results, but the method is not an absolute guarantee. A visual inspection of the experimental and library spectrum must be included.
So, to summarize what you should really take away from this entire process, a high probability score does not equal an absolute guarantee. Algorithms, no matter how advanced they get, cannot fully replace chemical intuition and contextual clues. Scientists must always keep a human in the loop to visually verify the computer's work side by side. The computer is an incredibly powerful assistant that narrows down tens of thousands of possibilities in a flash, but at the end of the day, the scientist is still the lead detective who makes the final call.
Which leaves us with this final thought. In a world of increasingly automated science, where artificial intelligence and these computerized spectral matching algorithms are getting better every single day, will human intuition ever be truly replaced? Or are we always going to need that human element to finally close the case? Thank you so much for joining me on this explainer. I hope you found this dive into the algorithmic mysteries of mass spectrometry as fascinating as I do. Keep asking questions, and I'll catch you next time.